Differential protection compares currents entering and leaving a zone. An internal fault creates a difference, triggering the relay. Its sensitivity and speed are defined by operating curves.
Why do we need protection systems? Because power equipment is expensive and faults can cause heavy currents, damage, fires, long outages, and financial losses. Protection isolates only the faulty section, keeping the rest of the system running safely. What is differential protection? It compares the current entering and leaving a protected zone. If both currents are equal, no fault exists. If the currents differ, an internal fault is detected. That's why differential protection is one of the fastest and most selective protection schemes. What is the protected zone? The protected zone is the section between CT1 and CT2 where currents are continuously monitored. It may include a transformer, generator, motor, busbar, reactor, or a large transmission line. Any internal fault within this zone is detected immediately. What is the basic principle of differential protection? According to Kirchhoff's current law, the current entering a protected zone equals the current leaving it under normal conditions. So I1 equals I2, the differential current is 0, and the relay remains stable. Now, let's see an internal fault. Current entering is 1200 amps, but only 150 amps leaves. So the differential current is 1050 amps. A large mismatch means an internal fault. The relay acts instantly and the circuit breaker trips. Now, let's look at an external fault. The fault is outside the protected zone, so the current entering and leaving are almost equal. The differential current is nearly zero. So, should the relay trip? No, it remains stable. That's why we call this property stability. Here's an important question. Why do we use a percentage differential relay? Because real current transformers are never perfectly identical. Ratio errors, saturation, magnetizing current, and different burdens can cause false differential current. So, we add percentage bias to prevent unwanted relay operation. Now, how does the relay make its decision? First, it calculates the operating current, the difference between the two currents. Then, it calculates the restraining current, the average of both currents. Finally, it compares these two values to decide whether to trip or remain stable. Here's the operating rule of a percentage differential relay. The relay trips only when the differential current is greater than the bias times the restraining current. Typical bias settings are 20, 30, or 40%. A higher bias means better stability and fewer false trips. Now look at the relay characteristic. If the operating point lies above the characteristic line, the relay trips. But if it falls below the line, the relay restrains and remains stable. Simple, reliable, and secure protection. Here's a key installation rule. Current transformers must be connected at both ends with the same ratio, correct polarity, and proper phase relationship. Why is this important? Because even a wrong CT polarity can create false differential current and cause an unwanted relay trip. Now, let's understand CT polarity. With correct polarity, the secondary currents oppose each other perfectly. So, what does the relay see? Almost zero differential current. That means the system is healthy and the relay remains stable without tripping. One of the most important applications of differential protection is transformer protection. It quickly detects winding faults, phase faults, earth faults, and turn-to-turn faults. The result? Fast relay operation that isolates the transformer and prevents severe damage. Transformer protection isn't as simple as it seems. A transformer introduces phase shift, ratio change, magnetizing current, and inrush current. So, can the relay ignore these effects? No, it must compensate for them to avoid false operation and ensure reliable protection. Now, what happens when a transformer is energized? A large inrush current flows containing a high second harmonic component. Modern numerical relays detect this second harmonic and block unnecessary tripping, keeping the transformer safely in service. Let's identify transformer inrush current. It has a very high magnitude, is rich in second harmonic, lasts only for a short time, and most importantly, it is not a fault. So the relay recognizes this condition and blocks unnecessary tripping. Now, let's look at an internal transformer fault. It may be caused by insulation failure, winding short circuits, turn insulation breakdown, oil deterioration, or mechanical damage. Since these faults are dangerous, the differential relay detects them immediately and trips without delay. Now, let's move to generator differential protection. It protects the stator winding against phase faults, earth faults, and coil faults. The best part, it operates extremely fast, typically within just 20 to 40 milliseconds, to minimize damage and keep the generator safe. Let's talk about busbar differential protection. A busbar connects many feeders, so a single fault can affect the entire substation. That's why differential protection responds ultra fast, isolating the faulty busbar immediately and protecting the whole system. Finally, let's look at motor differential protection. It is mainly used for large induction motors and synchronous motors. What does it protect against? Internal winding faults, phase faults, and earth faults. The relay detects these faults quickly and disconnects the motor before serious damage occurs. Modern numerical differential relays do much more than just trip. They perform digital filtering, harmonic restraint, adaptive bias, event recording, fault location, and even communicate with SCADA using IEC 61850. Smart, fast, and highly reliable protection. Why is differential protection so widely used? Because it's very fast, highly selective, sensitive, and reliable. It protects expensive equipment, offers excellent stability, and accurately distinguishes internal faults from external ones. That's why it's one of the most trusted protection schemes in power systems. Every protection scheme has limitations. Differential protection requires two current transformers with matching ratios, good CT performance, and pilot wiring. These requirements increase the installation cost, but they ensure highly accurate and dependable protection for critical equipment. Where is differential protection used? It's widely applied to power transformers, generators, bus bars, reactors, large motors, HVDC converters, and GIS substations. In short, wherever fast and reliable protection of critical power equipment is essential, differential protection is the preferred choice. Let's compare differential and overcurrent protection. Differential protection is a unit protection scheme, very fast and highly selective, but more expensive. Overcurrent protection is a non-unit scheme, more economical, but slower and less selective. Differential protection detects only internal faults, while overcurrent protection responds to both internal and external faults. Let's connect theory with industry. Popular numerical differential relays are available from Siemens Ciprotec, ABB Relion, GE Multilin, Schneider Mecom, SEL, Toshiba, and Hitachi Energy. These are the relay platforms you'll commonly encounter in modern power systems and substations. Before we finish, here's a quick challenge. Can you answer these interview questions? What is differential protection? Why is percentage bias needed? What is restraint current? Why is second harmonic restraint used? And finally, can you compare differential and overcurrent protection? If you can answer these, you're interview ready. Let's test your knowledge with a quick quiz. Differential protection works by comparing current or voltage. It's current. It's mainly used for internal faults. Transformer relays block operation during inrush current, and percentage bias improves. Stability. How many did you get right? Thank you for watching. If you found this lecture helpful, please like the video, share your questions in the comments, and subscribe for more electrical engineering lectures. Don't forget to explore our playlist for more power system protection topics. See you in the next lecture.